Welcome to the Futurati podcast. Any member of the Futurati is somebody who believes in the power of the future. We know there's a better world ahead, and we indeed have the power to make it so. In our podcast, we talk to the best minds in the world about the most urgent problems facing mankind today, and we hope you learn as much from them as we do. I'm Thomas Fry, a professional futurist and keynote speaker.
And I'm Trent Fowler, a machine learning engineer and author. Thank you for joining us. Good evening, everyone, and thank you for listening to the Futurati podcast. Today, we're interviewing my dear friend and former colleague, Dr. Erik Istre, who, in addition to being a software engineer, has done pioneering work on non-classical foundations for mathematics and naive set theory. Erik, thanks so much for joining us.
Thank you for having me.
Now, Tom, you'll be happy to know that earlier today, Erik and I were corresponding, and he said he was listening to our podcast and he found it, quote, pretty interesting. And so I don't know about you, but I think pretty interesting is where we should aim. That's kind of our speed. Because if he had said fascinating, that'd be a lot of pressure. Like, I don't know if I can be fascinating every week, but
yeah, we got to set the bar in the right level.
I think we could manage pretty interesting on a weekly basis. I think. So okay. Appreciate that honest feedback, Erik. And you and I actually have a pretty extensive history. So we went to the same college in Central Arkansas, and we didn't know each other there, but we had some mutual friends. And a couple years down the line, they said that we ought to talk to each other, and we hit it off. And then I think we began kind of corresponding seriously when I was in South Korea, and I'd become interested in artificial intelligence and existential risk and the whole penumbra of subjects around that. Mm-hmm. And you being almost cartoonishly generous, you agreed to kind of walk through this math text with me. And so I learned probability and basic logic and set theory, and all of that has kind of laid the foundation for the math that I know now. And then we worked together at Digital Assets Data, and then I moved on and you moved on, and now you're on my podcast. So it's great to get a chance to talk.
Yeah, I'm looking forward to it. I don't get to talk about my research much, so
yeah. So well, we're happy to give you the platform because it's really interesting stuff, and it's your thesis is 171 pages long, and if the audience doesn't know, that is a monster of a math thesis. So you get history theses or philosophy theses that are 800 pages, but a lot of math theses are like 20 or 30 pages. But Erik's is like it's a novel, and I mean I made it like 20 pages in and started getting nosebleeds. So.
Oh. Yeah, that's just like 3 prime numbers, and that's it.
It was quite the mountain to climb. So we're gonna have to do something a little bit different with this episode. We're gonna spend about 10 or 15 minutes, however long it takes, really, just kind of laying some foundations. And normally we don't do that. Normally we come right out of the gate and just talk about whatever comes up. But I think in this case we need to talk a little bit about the foundation of math, set theory, where your work comes in, the problems that it's trying to solve, and then we can kind of move into discussing applications and some of the deeper philosophical issues raised by the advances that you've made. So why don't we start off with a fairly straightforward question as these things go, and that's, what is a foundation of math, right? So we all count, we all add and subtract. What does it mean to have a foundation of math?
So when you're doing all of your mathy things, numbers and taking derivatives or whatever thing we want to talk about, you could just talk about those things as if they have an independent existence of their own. So you could say, well, there's a thing called 2 and there's a thing called 3, and that does some things and we can add them, etc. And you can define that. There came a point in the development of mathematics at which we were like, well, the existence of 2 and 3 and 4 and all that's cool, but how can we be certain that they exist in a sort of grounded way? And so foundation of math is about trying to define what I would call an ontology, the definition of the things that exist in your mathematical universe, and then how that ontology relates to each other. So what are the atoms, just like we talk about in physics, what are the atoms that make up the mathematical universe? And the important part is that you do that in a way that everybody kind of agrees to the basic atoms, and that there's a logic that is well defined, so that if you derive some mathematical truth, you can say, I got here by following these steps.
What is the motivation for working on that problem? What were the sticking points that arose such that it became important to answer these kinds of questions?
So I will just full disclaimer, I am not I'm not a historian of math. I have absorbed what I have through my years of doing math. But I think it comes a lot of it comes out when Cantor is starting to do his work on set theory. And he's doing these really crazy things with infinity. He's showing that there's multiple infinities. They're not just the one big thing. You get all of the interesting apparent paradoxes with infinity, like the hotel example in which you can just move everyone down a room and then create more space for everyone because you've already filled it, but now there's new room. So there's a lot of things that start to look a little bit funky, and there was the worry that we were starting to create mathematical realities that were not well founded, that didn't that you couldn't trace back their origin in a sensible way. So yeah, it started. This is where the history gets a little iffy, but that's essentially it. Where things started to get a little bit too crazy, and we were like, "Hey, let's figure out why we got to where we got there."
So, what are we looking for in a foundation of math? I guess I should ask it: what were they looking for in a foundation of math? Because we've got some twists to add to that. But as they were embarking on this project, what was it that they were trying to develop as a grounding for the rest of the project? Like, why was it not acceptable just to take a Platonist view and say, well, numbers exist in some kind of, ethereal separate realm, and that's how we ground them? Like, why doesn't that work? And what was it that they were trying to find?
Well, so you have Hilbert's program around that time, which was, I'm going to butcher this, like the 21 problems or something, where he laid out all of these very desirable things we want from math. Like he wanted to essentially be able to write for their time a machine that could prove any math theorem and that could derive a proof or show that any theorem you had was valid based on some axiomatic set and things like that. So what happened? So what they were trying to do, or can you repeat your question? I'm getting on a tangent.
No. So what was it that they were trying to build? So you've mentioned Hilbert's program. He had these 21 famous, I think it was 21 famous problems. These are things that we want to be able to solve. These are the aspects of a foundation of math that we want. And you were commenting on which of those properties were the ones that came first historically. So as people were building the foundations of math, what was it they were trying to accomplish?
Usually the phrase at the time probably was complete and consistent. You wanted something that captured all mathematical truths and something that did so in a consistent way so that you could be sure that you were not, and when they say consistent in the mathematical sense, they mean you do not derive that a statement is both true and false. And they wanted to be able to know for certainty that all of these wonderful informal mathematical theories we have been working with had a consistent basis.
So is it fair to say that after hundreds of years of pretty high-level mathematical development, these people were looking at what had come, and they were saying, we are coming a little untethered here, and we can't really be confident that when we prove a theorem, it actually means the thing that we think it means, or that it has any real relevance. And so we need to lay a foundation, put down some concrete for everything else to rest on. Is that a fair summary of it?
That is my apocryphal understanding.
And so when you're looking for a complete and consistent, would that be for any set of mathematical axioms? You could choose anything and then derive complete, consistent sets of sentences from those. Is that kind of?
So in general, when you're doing math, you're going to come up with some set of definitions that's going to define the things you're talking about. So you might talk about groups in algebra, or you might talk about what is a limit and what is a derivative. You're going to define those things very precisely. And you could proceed from there as if those were your axioms for that theory. And then when you're talking about a foundation of math, you're saying, what are the Godfather axioms? What are the axioms that I can use to define groups, and I can use to define limits, and I can use to define topological space? I can just I can have this one axiom set that is rich enough that I can define all of these other things I've been talking about this entire time.
Could you concretize that a little bit? What would an axiom consist of in a system like that?
I guess in an element of foreshadowing, there was in set theory, one of the axioms that was first proposed as a way to define set theory was the axiom of comprehension. And what that says, I mean, you can write it down in logic and do all these fancy things, but what it says in essence is that if you come up with some intention, which is just some meaning, some semantics, you can then collect all of the things that satisfy that meaning. So if I say all of the things that are red, then I can make a set which has all of the red things. Or if I say has the property is blue, etc. So it's just the way that would be an axiom. So we define that in logic, and it says if you have a property, I can get the things that satisfy that property.
Okay, and so from this, you want to be able to prove any mathematical truth, find them all in a way such that none of them contradict each other. Right.
So when we're talking in the context of set theory, that usually means that you're going to define the properties of a set that you're going to like say these sets over here that have these properties, well, these define groups or these define functions. And so you build up these sort of concepts of using this concept of set, how do I make a function? And that requires it requires a few concepts, but so I don't know if I should go into that. But it is just like you're having these very minute building blocks that the set concept is very broad. If you just think about what it means to have a collection of things, and it turns out by being so broad, it gives you a lot of power to just build these universes.
So my understanding is that the first attempt at solving these problems built upon set theory. Is that right? Why is set theory a better foundation for math than something like logic? Because that's what I would have assumed that it would be.
Well, so set theory is normally, I think, in almost all cases. I'm not going to say all because who knows. When you say set theory, you mean some axioms of set theory plus logic. So you will have some grounded sense of logic, normally classical logic, which dates back really, I think, back to Aristotle and stuff. Yep. I mean, it's changed a little bit since then, but you write down your classical logic. These are the valid rules of inference that you can use. And then you throw some axioms of set theory and away you go.
Okay. So they start with set theory. They have an idea of what they want to build. Can you, however fuzzily, walk us through what the succeeding decades look like?
So I think probably right at the beginning you had Frege doing his work, and he developed a really interesting system using set theory. There's something known as Frege's law, if memory serves, where he was essentially working what we would call now naive set theory, which uses this axiom of comprehension, which is super powerful, and you can just think up something and have a set. And it was found probably pretty quickly to have some problems. And then along comes Bertrand Russell and Whitehead, and they do their Principia Mathematica, and they are attempting to define, they use a kind of type theory, which I've never studied, but they're using a kind of type theory, as far as I can remember, which is a more computational way to do a foundations of mathematics. And they're trying to build up some stuff, and then basically what ends up happening is Frege's project explodes because of Russell's paradox, and Principia Mathematica explodes, mainly attributed to Girdle's results. And then you have Tarsky come along and throw further wrenches into the whole thing.
Okay. Well, let's take that bit by bit. So you said Frege's project was exploded by Russell's paradox. What is Russell's paradox?
Yeah, so Russell's paradox, the easiest place before I even talk about exactly Russell's that I like to start is the liar sentence.
Right.
Because most people are very familiar with that. So the liar sentence is the sentence that says this sentence is false.
Right.
And so importantly, the liar sentence is talking about itself.
Mm-hmm.
And in so doing that, you end up seeming to have to conclude that the liar sentence is both true and false. So the liar sentence says it is false. So if you assume that it's true, well, then because it says it's false, it has to have implied its own falsity as well.
Right.
And if you assume it's false, well, it says it's false, so therefore it's true. So if you kind of go with that idea, then Russell's paradox is the set which contains all of the things that are not members of themselves.
Oh, fun.
And then the question is, does the Russell set belong to itself? If the Russell set does belong to itself, then it can't belong to itself because it contains those things which don't contain themselves.
Right.
And then if it doesn't contain itself, well, then it has to contain itself because it contains those things which doesn't contain itself. So you get these weird sort of loops of logic which force you to conclude that the sentences are both true and false. So with the axiom of comprehension, it's super easy to build the Russell set. You literally basically just write in logic, you say X, not in X. It's all the things, all the sets that are not in themselves. And so that blew up Frege's project. And then,
right
there for that.
So it's there's this issue kind of embedded in the very attempt of logical systems to talk about themselves. And it's that when you have self-reference, any of these propositions have this flickering quality where they are both true and false at the same time, and it's very unsettling, and nobody's really sure what that means. Is that correct?
Yeah, and importantly, it's that, and that's when we get to Girdle and everything later, we start to realize that even if you try to restrict your axioms so much that you think you've gotten rid of all self-reference, with things like Girdle, it turns out that you can still make the system talk about itself if you're a little clever.
Well, Girdle was certainly a little clever.
Girdle was a little clever is an understatement, perhaps. Once the self-reference is sort of embedded in the system, once it has sufficient expressivity that it can define enough stuff.
Well, yeah, so let's go ahead and get into it. So Girdle's incompleteness theorem, why don't you just sketch that as briefly as you can and as simply as you can. What's the main result?
The summary, so normally when we say the incompleteness theorems, there's two of them. The summary, though, ultimately is taken to be the conclusion that there can be no complete and consistent system, formal system for mathematical truth or for arithmetic, whatever you want to talk about. The caveats are is the system has to be of sufficient expressivity and strength and all of this stuff, but it applies to a wide range of theories. If you want to do any interesting math at all, you have to have a system that will succumb to Girdle's incompleteness theorems, broadly believed. And so what it means to say that it can't be complete and consistent is that it can't capture all mathematical truth. If you attempt to capture all mathematical truth, it will force you to be inconsistent. If you want to be able to know it's consistent, then turns out that theory can't prove its own consistency. And so you have to go out of the theory, which gets you into all these weird situations in which you need theories proving other theories' consistency forever and ever and ever.
And I don't know that it will necessarily come across how monumental a result this was. That for, well, I mean, thousands of years, really. I mean, going clear back to Euclid, there was this hope that you'd be able to define a simple set of axioms and derive any mathematical truth you wanted to from it. And because it's math and it's pure and beautiful, it would be consistent. It would give you what you wanted. Yeah. And Girdle showed decisively that that is not the case and that it can never be the case. Is that right?
Yes. I mean, according to certain sets of assumptions.
Okay. And so You mentioned Tarsky earlier. We probably should cover that as well. Can you talk a little bit about
that? Yeah,
that?
Tarsky is really the meat of the matter to me at the end of the day.
Okay.
Tarsky proved what's called Tarsky's Undefinability theorem, in which he said essentially that a formal system could not have a truth predicate. So when we say predicate, that's another way of saying it describes a property. It's a predicate would be is blue. Tarsky showed that if you encoded something that did what you thought truth would do in a formal system, then you would be able to derive essentially the liar sentence in a formal system, because you would be able to build that self-reference, which said that the sentence talked about itself and made itself false. And so what ends up happening, and we enter into this world in math now in which, because a formal system cannot talk about its truth, you will have what's called a proof theory, the machinations, the machinery that you use to derive proofs. And then you will have a model theory, which provides semantic meaning for those random lines you're moving around on the page according to some set of rules. The model theory is what gives the truth, or the definition of truth, to that proof theory.
Could you say a little bit about how Girdle and Tarsky are related? Because I'm sort of having trouble distinguishing them in my mind. It sounds like Tarsky sort of extended Girdle's results, but I'm not totally confident that I have that correct.
So Girdle lived, his results applied to provability more blatantly. So you could kind of look at it as Girdle showed that the formal system couldn't do some of the nice things we wanted it to do, like prove its own consistency, or that there would have to be sentences that it could not prove to be true. And then I think it was pretty shortly after, Tarsky showed that, I guess not only that you couldn't even, like within your proof theory, you couldn't be nice and content, but that I take it as another way of saying you really have to go outside of your proof theory to get to the thing you want, which is some understanding of truth.
Okay. And so that was the state of things for a while. And then you began your research. So let's talk about your solutions to these problems.
Yeah. God, there's so much here. So as I said earlier, set theory is normally conceived of as being part logic and part axioms about sets. For what it's worth, I would be shunned perhaps if I did not mention that category theory and type theory are other two fairly popular foundations of math, and I have nothing against them. I'm not here for that feud. The very short, like 2-cent explanation is that also around the time you're doing all this formalization work, then intuitionistic logic comes out. And that's about, hey, everybody's using this classical logic. That's cool. There are some things I don't like about it. And they mess with the rules of logic. So they famously drop the law of excluded middle, which asserts that for any statement, it is either true or false. Intuitionistic logic says it might not be either, based on how you interpret it. So that is a very quick explanation. So that sort of opens the door to quite a few decades of logicians being like, hey, we can mess around with logic and see just see what happens. Fast forward to, I guess, more recently, turns out if you mess around with the logic enough, you can take those old naive set theory axioms, the ones that derive Russell's paradox, and you can get more content out of them. So you could try to avoid Russell's paradox deriving at all, so it's not true and false, or you could just make sure that when that happens, not all disaster strikes. In classical logic, there is what's known as explosion, which is the more colorful term. As soon as you derive a contradiction, it turns out with classical logic, you can then derive whatever you want. And you can write a logical proof for it. It's pretty simple. But essentially, once you have a contradiction in your system, you can no longer trust it. It just breaks. But that doesn't have to be the case.
So why was it not enough to have the intuitionistic logic? Is that intuitionist logic? Why was that not sufficient to solve some of these problems? You said you could kind of contain Russell's paradox. It wasn't a font disaster.
Intuitionistic logic still does not contain, still satisfies the principle of explosion.
Okay.
So as soon as it had a contradiction, it would still explode.
Okay.
And explode meaning it makes everything true.
Okay. So your work has focused on non-classical foundations of math and paraconsistent logic specifically. So let's get into what your proposed system and your proposed set of solutions to this problem is.
Yeah. So I did approach the research I originally got into was via what's called paraconsistency. So that is the idea that you might be able to hold in logical systems that something is both true and false and still be able to reason in some way. I'll give the caveat that you don't have to take like we can definitely talk about the semantic implications, which are very interesting, but just as like a matter of course, there are plenty of systems that exist in the world which will hold contradictions that you might want to be able to reason about, even if you're not asserting that the world itself is both true and false in some cases. So paraconsistency says, well, so we can have some contradictions, and so then we can throw these really expressive axioms from naive set theory. So that's the axiom of comprehension and the axiom of extensionality, which is in all set theories. Of course, not all. Everybody does something, whatever they want, but two sets are equal if they have the same things. And so there's one way to go about trying to salvage naive set theory is a paraconsistent approach. That's where my work started, and what falls out is, in fact, I guess, paraconsistent in a certain sense. But it's not because I'm making a strong claim anymore about whether true and false things are. It's a little interesting. I don't know, but yeah.
Okay, so one question I have is how is it that a paraconsistent system contains the explosion? How is it that it has contradictions but still preserves the ability to reason about things without everything then becoming true?
Well, in your question lies the struggle in trying to do research like this, because basically the truth is if you want to reason in a system that derives a contradiction, then you have to get rid of the principle of explosion. In which case we start to say that we've now separated the concepts of triviality, everything is true, from the concept of inconsistency. In our old systems, those were one and the same. As soon as you had an inconsistency, they were trivial. So you can avoid the principle of explosion by getting rid of other logical rules or things that we're used to. There are a lot of different approaches to this. And in effect, though, you are hamstringing your options. You are weakening your system purposefully to try not to end up in a trivial state. So it does make reasoning a lot harder. And that is true against all approaches. There's something called weak relevant logics. There's something called light linear logics. And then there's my approach, which really fits into a school of thought known as cut-free theory.
Okay. So could you give us a sense of where your research ended up? I mean, sorry to tell you, I didn't make it all the way through your thesis. So could you fast forward to the end and tell me how it ended up?
So I ended up in the, I guess, cut-free school.
Okay.
So the system still derives contradictions. It'll derive that Russell's set is in itself and not in itself. And we can talk about what my semantic understanding of what that means about the mathematical universe. But cut-free, so cut refers to a logical rule in what's called sequent calculus, a bunch of words. Cut is essentially transitivity. So if A implies B and B implies C, then A implies C.
Right.
That's transitivity. Cut is essentially an encoding of that. And a cut-free system will not assume cut at the outset. So it will say, transitivity is totally nice, and it's really hard to do away with. We want transitivity. But rather than, basically my approach is saying, rather than assume transitivity from the outset, let's let it be something that can be derived for subsections of the theory. And I'm fairly, of course, I mean, this is my research, I am fairly adamant that is the correct approach to take with transitivity. That it's not something you can just assume to apply. You actually have to prove it applies to certain parts of your theory.
Very interesting. Yeah, it's one of those things that seems just kind of so obvious that it's hard to imagine a theory that forces you to prove that about sets of objects in the mathematical universe.
Yeah. So what ends up happening is, so transitivity, we like have this informal notion that transitivity is true because it sure seems like I can prove that to you. Like I can say, well, I've got a proof from A to B and I have a proof from B to C. So just glue them together and you got a proof from A to C, you're done. That's an informal proof. If we're formal mathematicians, we need a formal proof of things.
Yep.
And it turns out when you have a really expressive theory, you can form sentences which don't satisfy transitivity. Russell said, when you actually do the proof of Russell's paradox, at the part where you would descend into trivial madness, if you don't have cut, you can't do that. It's just like, it's almost too simple, I think, is why it's, I think people are skeptical.
It sounds
of
too
it.
simple, yeah. It sounds really simple.
But it's...
yeah, if I could, I'd like to pose a scenario and just see how you would go about solving it, because I'm working as a futurist, and I'm kind of obsessed with this idea of where does the future come from, and do all of the inertias of things that are presently happening, is that what's taking us into the future, or is there some cosmic force that's pulling us towards it? And how would you go about reducing that to a set of assumptions? And maybe this is way out of what you're normally wrestling with. But.
So, I mean, ironically, I was thinking about time the other day, but for completely unrelated reasons.
See, I can predict a lot of things about the future with a high degree of probability. I can predict that the Earth's going to travel around the sun in roughly the same orbit, 100 years from now, with a high degree of probability. I can predict that the building that we're in is going to still be here 6 months from now, with a high degree of probability. And so there's lots of things that we can predict with a high degree of probability. And so most of the future is built around stable, slow-moving parts. And in fact, I can plan a birthday party 2 weeks from now, and I can plan it in a way that I can have confidence that it's going to take place, because there's enough stable elements in the world around me that I can count on to make that happen. The things that are most unpredictable have to do with humans and animals and weather and forces of nature, that sort of thing.
I mean, when I tend to think about things and I guess, this gets into some like fundamental, like philosophical questions. Do you believe the universe is deterministic? And then in regards to my particular research, I don't have a way to apply it to this question, though there may be interesting ways to do so. That's mainly just me thinking about, like, in my head, everything's a chaotic dynamical system, and if you had the initial conditions right, you would be able to figure out what's going to happen. Good luck getting those initial conditions, though. It's just not going to happen.
Or understanding the dynamics that drive how the system evolves over time.
Yeah, the rules are so complex that I think it's beyond many intelligent agents, if not all. I don't know. But
well, there is one way that your work can kind of bear on the future, and that's in discussing some of the practical applications of it. I almost hesitate to even say practical exactly, but
practical. I think of interest probably to this particular podcast is what implications it would have for formal artificial general intelligence study.
Yeah, systems that reason about themselves and recursively self-improve. So presumably you've got some thoughts on that. Why don't you just take it away?
Essentially what happens is you revise Girdle's disjunction, I guess, if you will, of that if you want complete, that you're forced to choose complete or consistent, and we normally choose consistent. The assertion would be that with a system of my variation, or I'm not the only one to work on cut-free systems. To my knowledge, I'm the only one who's done it extensively with naive set theory. That's about the only difference. That you could have a complete system of mathematical truth, and it's inconsistent. There are some things which are true and false. That ultimately gets me interested in, well, this is more mathematical things. So in regards to AGI, I know that some formal AGI research, some of which I've looked at and one day hope to be able to apply my work to, is concerned with that if you're going to build a formal agent, you want to be able to verify that it's going to do the things you think it can do. Because of Girdle's incompleteness theorems, or particular lube, I think is actually how you're supposed to say it. I'm really bad about names. Because of his theorems, you end up in weird places, like you need an infinite descending chain of theories verifying other theories which are weaker, so that you can be certified. Like you get into these places where, like, to be certain that you know what the agent is going to do requires you to meet certain requirements that are just sort of obnoxious. Where the system I worked on is very easily provable to be non-trivial. And again, it's just like, it feels like you're cheating because you don't have cut. You can very easily derive that the system doesn't prove something. In fact, like that's what we have consistency proofs throughout mathematics. Like we have a consistency proof of piano arithmetic. And what you do to derive those proofs is you do what's called cut elimination. You prove that you can remove cut and still derive the same things. It just turns out that sometimes you can't do cut elimination on finite times. You have to do infinitely descending or inductive proofs. So by not having cut from the beginning, it's just trivially the case that there is something you can't prove. So we know that the system is non-trivial. And then I have a rather, I have an argument that is probably not well received by most people in the field, that something like what I call normalized naive set theory in my thesis is as close or is complete mathematical truth encoded in a theory.
Well,
we could go into that.
Let's go ahead and get into it.
This goes back to the Church Turing thesis, which is that essentially asserts that any informal computation we can do can be captured by our formal notions of computability. So a Turing machine, or lambda calculus, or primitive recursive arithmetic. The Church Turing thesis is not something you can prove because it is making a statement about the informal relationship to the formal. So you can't ever be certain that it's true. We seem to have pretty good inductive evidence because every time we come up with a new model of computation, we end up right back where we started. Turing machines are equivalent to lambda calculus, or equivalent to, et cetera. So then, I haven't trudged this argument out in a while. You don't want to be the crazy mathematician.
Right.
So there's another bit of equivalence that we've learned to believe has to be false because of Girdle's incompleteness theorems. So that is the claim that any proof is an effective computation, and any effective computation is a proof.
Oh, okay.
So any effective computation is a proof. You can't really argue with that. That's like, I derived that 33 plus 56 equals
whatever
89 maybe. And I wrote it down and I could show it to you and you're like, hey, that I see what you did. That's deterministic. This is readable by other intelligent agents. Like it fits all the things that you would call a proof. But it turns around, if you go the other way and you say that any proof is an effective computation, you run into problems, because if any proof is an effective computation, then that normally takes it to mean that you could express it in a Turing machine or in your formal notions of computability. Oh man, I have to try. I almost might need to pull out my thesis for this because I haven't talked about it. This might be a cut point for a second.
Yeah, that's okay.
Because I have to pull in, the way the argument goes, I pull in Church-Turing thesis, I pull in any proof is a effective computation. Then there's also the Curry-Howard isomorphism. It's a lot of steps. Maybe I should just shorten that somehow. I think I'm getting a little too mathy.
Yeah, well,
Does
that's
it feel like
to
I'm
be
being too
expected.
mathy?
It was. I mean, I'm fine with it, but yeah, maybe we skip Curry-Howard.
So if we're talking about why my system would have all of mathematical truth, is that what we're trying to get at?
Well, it's yeah. What is it that your system gets that we couldn't get somewhere else? Like, why buy from you?
Yeah. I'm gonna have to pull out my thesis once again.
We asked interesting questions, yeah. I especially like the 33 plus 56, and we're all like, it's 80, 89. Yeah, that's it. It's 89. We're all sitting around like trying to do basic arithmetic.
Like I said, in an effort to not be the crazy mathematician, I don't spend much time thinking about these arguments anymore. I'm just trying to prove stuff about my naive set theory.
Well, if you want, why don't we just count everything up to this point as a preamble and a rehearsal? And my original question was, you said something about you having an argument for your approach being the way to do this. So why don't we just pretend I just asked that question?
Okay.
And then you just kind of lay out the whole case as you began to do.
Trying to get, yeah, that'll be too logically. They can look it up in my thesis if they want. At a higher level, I'll go there. Okay. So the reason you might want to use a system like the one I developed is if you're interested in the foundation of math, our available options are pretty good, but they end up falling short for various reasons. So things like the weight of having to think about the fact that if you want to do things in a reasonable way, you might need an infinite descending chain of theories which prove each other's. Like what ends up happening is you need a theory that has truth for another theory, which has truth for another theory, and it's just
right
madness. And it's intuitively all of these constructions that are quite clever and very interesting are not things that we do when we think about truth naively, and we're forced there because of Girdle's incompleteness theorems, ostensibly. Well, with normalized naive set theory, you accept that you have an inconsistent theory, but in return, you get, if we're talking about naive set theory, you get more expressive power than is available in any existing foundation of math. So it's very easy to, with the axiom of comprehension, define whatever set you want. And there are some like limitative results. Like when we're talking about category theory, there are some really big categories that we want to make. And it's really hard to verify that you can do those with the set theories we normally use. For example, you end up in places where you almost have to come up with something really clever, or you just have to hand wave it away and say, we'll figure out why that's formally valid later.
Okay.
With naive set theory, there's none of that because the axiom of comprehension says I can get a set for anything I want.
So with social media right now, they're trying to apply a truth meter to everything that's being posted. Can you comment on how that would fit into your thinking and how you would go about managing a process like that?
So I still believe, despite my mathematical theory, that the physical world and its semantics are consistent. So I think there is a truth or a falsity. I mean, obvious gradations, need for clarity, et cetera, et cetera. I mean, I would think there is a true and there is a false of an event that happened, assuming the sentence is clear enough.
Yeah, well, that's actually an interesting segue into discussing the philosophical ramifications of this work. So if it is a viable foundation for an agent that's reasoning about itself and recursively self-improving, then why is it not also a good description of reality? Like, how is that bifurcation achieved in the agent? It's using normalized naive set theory, your system, which sacrifices consistency for completeness, to update its own code, to reason about itself and its successors and what they will want. But then when it reasons about the universe that we all occupy, it's using something a lot more like naive set theory, where there are truths and falsehoods and many of these problems don't arise. So, I mean, how does that work? What does that mean?
Yeah, so the way I've taken to understanding the existence of inconsistencies in systems like mine is that you are describing possible worlds, essentially. That word is a little loaded, so I'm not quite sure I want to use it, but you can derive, Russell said, is in itself and not in itself. But those atoms of the theory can't interact in any meaningful way because of the lack of cut. So essentially what you could do is say, well, I'm going to work as if Russell set is in itself, and I'm going to build a sub-theory of this massively expressive theory and see what happens when Russell set is inside itself. I mean, Russell set isn't that interesting beyond the paradox in ways that I know. But like, if you wanted to have that truth in your system, you could say, I'm going to work with that. So essentially, the way I approach it is that this normalized naive set theory is all possible models, and you're just going to find the one that applies to your physical world.
Okay, so the space of models that your system can talk about is far larger than what we actually find in our universe. We're constrained to a universe in which...
I mean, as far as I'm aware, I would expect that the mathematical universe is far more broad and weird than what we get in our day-to-day life.
Yeah, so one thing I've always been curious about, ever since I learned of this work, and you and I discussed it years ago, is what it means metaphysically. So I'm fairly Aristotelian in my approach to logic and philosophy. I tend to put a lot of stock in the basic laws of logic as Aristotle laid them out. You've got the law of non-contradiction and the law of the excluded middle and the law of identity. It sounds like normalized naive set theory isn't really a challenge to any of those things. It's only something that you pull out when you've got these really twisty logical systems talking about themselves and trying to avoid descending into an infinite chain of theorems, proving theorems about each other. But for the rest of us, for the rest of the time, we just don't have to worry about it. Like we're fine being Aristotelians. Yeah. Is that basically the case?
The main result of my thesis beyond exploring this theory is I show that you can recover second order Heyting arithmetic, which is a particular subtheory of arithmetic, et cetera, et cetera. Basically, that says that you can do a lot of math in here if you want. And if you're doing math in this subsection known as Heyting arithmetic, then I think I'm saying his name wrong. I'm so sorry. If you're doing math there, you have cut again. It's all fine. You can go about your day. And it's believed that one of the things I'm working on is extending that to what's called second order piano arithmetic. And once you can do that, that's most of the math that we care about, unless you're a mathematician. So it's just the big theories there as a way of saying, here's all of these other things that you could possibly make models for. But for most of us, it's not going to affect our day-to-day semantical understanding of what's going on around.
So isn't a lot of this handled by probabilistic reasoning systems? Like, why can't we just escape some of this by attaching probabilities to the conclusions that we draw, or our assessment of whether something is true or false? Like, why wander off into these ontological thickets?
I'm not I haven't studied probabilistic logic very much, but I would imagine the ultimate problem you're always going to face is, and there's a word for it, but I can't think of it, in which your probabilities would go to zero once you chain them long enough. Like you're talking about developing a model of the world is going to be very complex. And so if you're trying to integrate long chains of probabilistic inference, I think you're probably going to reasonably quickly run into problems in which your probability for an event happening is going to zero. And then you're sort of out of luck. At another level, I just like deductive reasoning.
Because I had nothing better to do.
I mean, it's like there's like I am a pure mathematician in a lot of senses of the word, and what that means is I thought this was pretty cool and interesting, and so I looked at it, and it seems like it has interesting philosophical interpretations or implications for what happens with Girdle's incompleteness theorems, which I like because Girdle is my hero, and so I want to be able to destroy his work. It's just the way it happens.
Well, that's fantastic. In the last 9 or so minutes that we have, why don't you tell us a little bit about where you plan on taking this work?
So there's a big thing I need to do to verify a certain thing, which is I want to get a lot closer to making that argument a lot cleaner about my system can capture all mathematical truth. So the very next thing I have to do is show that if you can think of a formal computer program, I can manipulate the atoms of my set theory in such a way that I can produce it. So there's nothing you can do that computationally is not available to it. And what that means is that it has, in theory, all possible computational power when computing proofs. Then after that is when I'm going to sit on an armchair and think deeply about what this does with things like girdles, but also a question I'm really interested in as well as what it does with infinities. So diagonalization argument is the way that Cantor proves there's more infinities than just the countable one. Those kind of arguments break apart when you don't have transitivity. So you might only have one infinity, or you might conclude that you might have one infinity, you might not, you both have multiple infinities and you only have one, something weird like that. And then you could explore what that does. Another thing from like a broader perspective is there are things which are known to be independent of common set theories. One is the Continuum Hypothesis. And I'm very curious whether you could prove it's both true and false in this system. So we know it's independent of these other systems. Maybe what that comes out as in this theory is take your pick. Do you want it to be true? Do you want it to be false? And then develop your sub-theory as you want. And then once all of that, I'd be very curious to apply it to problems that I'm tangentially aware of in the AGI community with formal reasoning.
Yeah, we had a conversation with a gentleman who is he's a very funny guy, but he was a fatalist as we were talking about artificial general intelligence, and I've not run into funny fatalists before. It's a bit of an anomaly. So with artificial general intelligence, how do you see that playing out in what laws apply and don't apply as that unfolds?
So I think using something like the system, you could develop very reasonable, formal definitions of agent self-improvement and all that. I don't consider myself qualified enough to say whether formal AGI is the way to AGI because I am not an artificial intelligence expert. But being aware of the problems I do know in AGI, being able to a lot more succinctly say, this is how my formal system will prove that the next one it can be verified. And in fact, it's not the next one. It's the system can talk about itself because it's so expressive, and it could find the new sub-theory within itself, and just you only have to live in that theory rather than creating new ones. So for an agent that's building some sort of formal understanding, in theory, it's all already there. All the atoms that it would need to rearrange to figure out what it should do next in improving itself are already contained.
But how does it accomplish that? I mean,
that I don't know. I mean,
but how does it cause? I mean, everything degradates over time. It falls apart over time.
Or the systems become weaker, the logical system.
Yeah. How do you keep rebuilding yourself?
Well, they're believed to become weaker because of issues like Loop's theorem, which are not no longer apply. Those are gone.
Okay, so you circumvent some of that.
So like of the research I'm aware in which they have to continually make weaker and weaker systems, they are doing that because they've succumbed to that limitative result. And that limitative result doesn't apply to the system, of which I'm pretty confident because it's very easy to derive sentences which do what lobes do because you have the axiom of comprehension. That's actually a whole other conversation. There's something called Curry's paradox, which is the bane of my existence, actually.
You ought to consider looking into some of the research being done at MIRI, the Machine Intelligence Research
Yeah, that's
Institute.
what I've read before.
One of the papers I read, one of the papers I skimmed, one of the papers I attempted to read in preparation for this interview was on tiling as a solution to solving this issue where you've got an infinite chain of agents reasoning about each agent and some of the things that come out of that. And Loeb's obstacle was specifically a thing that they were trying to address in the paper.
And then this is why I say Tarsky is so important to me. Like the system can define a truth predicate. It's really easy. And so you have a formal system which can know and talk about its own notion of truth. I'm using talk it's not really talking, but but it can define truth and it can operate on it. You no longer have to live in this world, which we live in for a century, of like, my formal system can't know its own notion of truth. It can very easily define it. It can define its own notion of provability. It's all just right there. So there's a lot which like it turns on its head because we're so used to thinking in like, well, if I'm going to verify my system, I have to go outside the system because it can't prove its own consistency or it can't do its own notion of truth. All of that goes away. There's just the one, which I guess if I have no other platform to ever say this is how you end postmodern thought. So here's my solution to postmodernism. The movement from postmodernism is not that. So you have modernism where and this is my own take on it, but where you have all your formal axioms and you're trying to define things very particular. And postmodernism is like, hey, all of our axioms are up in the air and you could choose some and you could leave some. And how can we agree on any common ground of truth? The solution is a system like naive set theory, which can express all theories. So you can now agree on fundamental truths. We can then use the massive amounts of expressivity in those truths to make models of any other truth system that you want. And then you're all in the same system to talk about your different theories. So you have a formal rebirth. There's formalism at the bottom, but you can also make models of all other theories and talk about them within the same framework. That is my solution to postmodernism.
Well, that is fascinating and provocative. It horrifies me that
you don't have to put that in the podcast.
No, it's just a shame that you brought that up when we have 60 seconds left to go because there's just so much fertile ground there. But this is absolutely fascinating. I know that your thesis exists online. I mean, is that where you would point people if you wanted to punish them? It is quite it's very impressive and very fascinating. So thank you so much for.
I am working on a revised version and improving my proofs, which, given that I am haphazard in my approach, and maybe years, who knows?
Well, excellent. We will all look forward to that as if it were another Harry Potter book. And Dr. East, thanks so much for joining us today.
Yeah. How do people get in touch with you?
Oh, sure. I mean, they can just email me. That's fine. I don't know. I'm not very fancy. e.istre91@gmail.com.
All right.
Is that a bad idea to put on a podcast? I don't know.
Well, that remains to be seen. This will be our test.
Okay, let's do it. Let's see what happens.
Awesome. Thanks very much, Erik.
All right. Thanks.
There you go.